Hey there, Internet explorers and digital dreamers. Ready to unravel the mysteries of the online world? Welcome to Network Nutters, where Wi-Fi is life and buffering is the enemy. Ever wondered how your cat videos travel across the globe faster than you can say, viral? Or why your Wi-Fi decides to take a coffee break just when you're about to win that online game? Well, you're in for a treat. In the next few minutes, we're going to zoom through the wild world of computer networking. From IP addresses to the Internet of Things, we'll decode the digital magic that keeps our modern world spinning. But before we dive in, don't forget to hit that subscribe button. Trust me, your future tech-savvy self will thank you. Plus, it helps us reach more curious minds like yours. Ready to get this show on the information superhighway? Let's go!
That was a fun start, wasn't it? Now let's get to the serious stuff. Welcome to our journey through the world of computer networks. In this slide, we'll explore the basics of what networks are and why they're important. Computer networks are systems that allow computers to share information and resources. Think of them like a group of friends passing notes to each other. Networks come in various sizes, from small home networks to the vast internet that spans the globe. We use networks every day without realizing it. When you send an email, browse a website, or stream a video, you're using a network. Networks make our digital world possible, connecting devices and people across vast distances. There are different types of networks, each serving a specific purpose. Local area networks, LANs, connect devices in a small area, like your home or office. Wide area networks, WANs, connect devices across larger distances, even between countries. Now that we understand what networks are, let's dive deeper into how they're structured. In our previous slide, we learned what networks are. Now let's explore how they're organized using network models. Network models are like blueprints that show how different parts of a network work together. They help us understand the complex process of data transmission by breaking it down into simpler steps or layers. There are two main network models: the OSI Open Systems Interconnection model and the TCP/IP model. The OSI model has 7 layers, while the TCP/IP model has 4. Each layer in these models represents a specific function in the data transmission process. Think of these layers like an assembly line in a factory. Each station or layer has a specific job to do before passing the product or data to the next station. This organized approach helps in designing, troubleshooting, and understanding networks. The OSI model's 7 layers are physical, data link, network, transport, session, presentation, and application. The TCP/IP model simplifies this into 4 layers: network interface, internet, transport, and application. Understanding these models is crucial for anyone working with networks. Now let's start our journey through these layers, beginning with the physical layer. We've just learned about network models. Now let's zoom in on the foundation of all network communication: the physical layer. The physical layer is the first layer in the OSI model. It deals with the actual physical connection between devices. This is where electrical pulses, light signals, or radio waves come into play. When you plug an Ethernet cable into your computer or connect to Wi-Fi, you're interacting with the physical layer. It's responsible for transmitting raw bits, ones and zeros, from one device to another over a physical medium. This layer defines specifications for cables, network interface cards, and wireless technologies. It handles aspects like voltage levels, data rates, maximum transmission distances, and physical connectors. The physical layer doesn't understand the meaning of the data it transmits. Its job is simply to get the raw data from one point to another reliably. It's like a delivery truck that doesn't care what's in the packages it carries. Key technologies at this layer include Ethernet, Wi-Fi, Bluetooth, and fiber optics. Each of these has its own set of standards for how data should be physically transmitted. Now that we understand how data is physically transmitted, let's move up to the next layer to see how this raw data is organized and checked for errors. We've seen how the physical layer transmits raw data. Now let's explore how the data link layer organizes and checks this data. The data link layer is the second layer in the OSI model. Its main job is to make sure data is delivered reliably between two directly connected devices. It's like a careful postal worker who ensures packages are correctly addressed and undamaged. This layer takes the raw bits from the physical layer and organizes them into larger units called frames. Each frame typically includes the sender's and receiver's physical addresses, MAC addresses, the data itself, and error checking information. One of the key functions of the data link layer is error detection and correction. It checks if data has been corrupted during transmission and can often correct minor errors or request retransmission if necessary. The data link layer also handles flow control, ensuring that a fast sender doesn't overwhelm a slow receiver with too much data at once. It's like making sure you don't talk too fast for your listener to understand. Common protocols at this layer include Ethernet for wired networks and Wi-Fi for wireless networks. These protocols define how devices should format data and take turns using the network. With data now organized into frames and checked for errors, we're ready to move up to the network layer, where we'll learn how data finds its way through complex networks. We've seen how the data link layer organizes data into frames. Now let's explore how the network layer helps these frames find their way across complex networks. The network layer is the third layer in the OSI model. Its primary function is routing, determining the best path for data to travel from its source to its destination. It's like a GPS system for your data packets. At this layer, each device is assigned a unique logical address, known as an IP address. These addresses are crucial for routing data across different networks. When you send data to a website, it's the IP address that helps your data find its way there. The network layer breaks data into smaller units called packets. Each packet contains not just the data, but also the source and destination IP addresses. This allows each packet to be routed independently, potentially taking different paths to reach the same destination. A key device at this layer is the router. Routers use complex algorithms to determine the best path for each packet based on factors like network congestion and connection speeds. The most common protocol at this layer is IP, Internet Protocol. There are two versions in use, IPv4 and IPv6. IPv6 was developed to address the shortage of available IPv4 addresses as more devices connect to the Internet. With our data now packaged and addressed for its journey, let's move up to the transport layer to see how it ensures our data arrives intact and in the right order. We've learned how the network layer routes our data. Now let's see how the transport layer ensures this data arrives correctly and in order. The transport layer is the fourth layer of the OSI model. Its main job is to provide reliable data transfer services to the upper layers. Think of it as a shipping company that handles the logistics of your data delivery. This layer breaks large messages into smaller segments, which are easier to transmit and manage. It also handles reassembly of these segments at the destination, ensuring they're put back together in the correct order. There are two main protocols at this layer, TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP is like sending a package with tracking and delivery confirmation. It's reliable but slower. UDP is like regular mail, faster but with no guarantees. TCP provides features like error checking, acknowledgement of received data, and retransmission of lost data. It's used for applications where accuracy is crucial, like web browsing or file transfers. UDP, on the other hand, is simpler and faster but less reliable. It's used for applications where speed is more important than perfect accuracy, like online gaming or streaming video. The transport layer also handles flow control, ensuring that a fast sender doesn't overwhelm a slow receiver with too much data at once. It's like making sure a conversation is at a pace both parties can handle. With our data now segmented, ordered, and ready for reliable transmission, let's move up to the application layer to see how our everyday apps interact with the network. We've seen how lower layers handle the nitty-gritty of data transmission. Now let's explore the application layer, where our everyday apps interact with the network. The application layer is the topmost layer in both the OSI and TCP IP models. It's the layer closest to the end user, providing network services directly to applications. Think of it as the user interface of our networking system. This layer defines protocols and rules for how applications should communicate. Common protocols include HTTP for web browsing, SMTP for sending emails, FTP for file transfers, and DNS for translating domain names to IP addresses. When you open a web browser and type in a URL, you're interacting with the application layer. It takes your request, formats it according to the HTTP protocol, and sends it down through the other layers for transmission. The application layer also handles things like data formatting, encryption, and session management. For example, when you log into a website, the application layer manages your session to keep you logged in as you navigate different pages. It's important to note that the application layer in the network model is not the same as the applications themselves. Rather, it provides services that applications can use to access the network. Some other important protocols at this layer include SSH for secure remote access, DHCP for automatic IP address assignment, and POP3 and IMAP for receiving emails. Now that we understand how data moves through the network layers, let's take a closer look at how devices are identified on a network with IP addressing. We've explored the layers of network communication. Now let's focus on how devices are identified on a network using IP addressing. IP Internet Protocol. Addresses are unique identifiers assigned to each device on a network. They work like postal addresses for computers, ensuring data reaches its intended destination. There are two versions of IP in use today, IPv4 and IPv6. IPv4 addresses are 32-bit numbers usually written as four numbers separated by dots, like 192.168.1. IPv6 addresses are 128-bit numbers written in hexadecimal, like example given in the slide. IPv4 is still widely used, but with the growing number of internet-connected devices, we're running out of available addresses. That's why IPv6 was developed, offering a vastly larger address space. IP addresses can be static, permanently assigned, or dynamic, temporarily assigned by a DHCP server. Most home devices use dynamic IP addresses, while servers often use static IPs. IP addresses are divided into classes, A, B, C, D, E, based on their first few bits. This classification helps in efficient routing and address allocation. There are also special types of IP addresses. Private IP addresses are used within local networks and can't be accessed directly from the Internet. Public IP addresses are globally unique and used for Internet-facing devices. Understanding IP addressing is crucial for network configuration and troubleshooting. It's the foundation of how devices find each other on the vast network that is the Internet. Now that we know how devices are addressed, let's look at how large networks are divided into smaller, manageable parts through subnetting. We've learned about IP addressing. Now let's explore how large networks are divided into smaller, manageable parts through subnetting. Subnetting is the practice of dividing a large network into smaller subnetworks, or subnets. It's like dividing a large office building into smaller departments for better organization and management. The main reasons for subnetting include improved network performance, enhanced security, and more efficient use of IP addresses. By creating smaller network segments, we can reduce traffic congestion and isolate potential security threats. Subnetting works by borrowing bits from the host portion of an IP address to create additional network bits. This is done using a subnet mask, which determines which part of an IP address identifies the network and which part identifies the host. Network administrators use subnetting to optimize network design, improve security by segregating sensitive parts of the network, and make more efficient use of limited IP address space. Understanding subnetting is crucial for anyone working with networks, especially when configuring routers and planning network expansions. Now that we've seen how networks are divided, let's explore how data finds its way through these complex network structures through routing. We've learned about subnetting. Now let's explore how data navigates through these complex network structures through routing. Routing is the process of selecting paths for data to travel across a network. It's like a GPS system for your data packets, guiding them from their source to their destination through the most efficient path. At the heart of routing are devices called routers. Routers are like traffic cops at intersections, directing data packets based on their destination IP addresses. They maintain routing tables that list available paths to different network destinations. There are two main types of routing: static and dynamic. Static routing involves manually configuring routes, which is suitable for small, unchanging networks. Dynamic routing, on the other hand, allows routers to automatically adjust to network changes. Dynamic routing protocols like RIP, Routing Information Protocol, OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol, allow routers to share information about network topology and select the best routes. Routers make routing decisions based on various factors, including the number of hops, intermediate devices, to the destination, line speed, and network congestion. The goal is to find the most efficient path, which isn't always the most direct one. Internet routing is particularly complex, involving multiple autonomous systems, as networks under a single administration. BGP is used for routing between these systems, forming the backbone of Internet communication. Understanding routing is crucial for network design and troubleshooting. It's what makes it possible for data to find its way across the vast, interconnected landscape of the Internet. Now that we know how data is routed, let's look at how it's managed within local networks through switching and VLANs. We've explored how routing guides data across networks. Now let's focus on how data is managed within local networks through switching and VLANs. Switches are crucial devices in local area networks, LANs. Unlike hubs that broadcast data to all connected devices, switches intelligently direct data only to its intended destination. They do this by learning and maintaining a table of MAC addresses associated with each of their ports. When a switch receives a data frame, it looks at the destination MAC address and forwards the frame only to the port where that device is connected. This reduces network traffic and improves overall network performance. Switches operate at the data link layer of the OSI model, making forwarding decisions based on MAC addresses rather than IP addresses. This makes them faster and more efficient for local network traffic than routers. VLANs, or virtual local area networks, are a way to logically segment a network without changing its physical structure. They allow network administrators to group devices together, as if they were on separate physical networks, even if they're connected to the same switch. VLANs offer several benefits: improved security by isolating sensitive parts of the network, better performance by reducing unnecessary traffic between network segments, more flexible network design, as devices can be grouped logically rather than by physical location. Switches that support VLANs can tag frames with VLAN IDs, allowing them to keep traffic from different VLANs separate, even when it's traveling over the same physical links. Understanding switching and VLANs is crucial for designing efficient and secure local networks. They form the backbone of most enterprise network infrastructures. Now that we've covered wired networking concepts, let's move on to explore the world of wireless networking. We've discussed wired networking. Now let's explore wireless networking, which has revolutionized how we connect devices. Wireless networking allows devices to communicate without physical cable connections. The most common form is Wi-Fi, which uses radio waves to transmit data. Wi-Fi operates on 2.4 GHz and 5 GHz frequency bands. Standards like 802.11n, 802.11ac, and Wi-Fi 6 define speeds and features. Other wireless technologies include Bluetooth for short-range communication and cellular networks, 3G, 4G, 5G, for mobile devices. Security is crucial in wireless networks, with protocols like WPA2/WPA3 encrypting data to prevent unauthorized access. Now let's explore how we keep these networks safe with network security. As we've explored networking, it's crucial to discuss how we keep these networks safe. Network security protects the integrity, confidentiality, and accessibility of computer networks and data. Key security measures include firewalls, monitor and control network traffic, encryption, scrambles data for secure transmission, virtual private networks. VPNs create secure connections over public networks. Intrusion detection/prevention systems monitor for and block suspicious activity. Regular security audits, software updates, and user education are also crucial components. As threats evolve, network security remains an ever-changing field. Now let's explore how we translate website names into IP addresses with DNS. We've learned about securing networks, Now let's explore the domain name system, DNS. DNS translates human-readable domain names, like www.example.com, into IP addresses that computers use. The DNS system is hierarchical with root servers at the top, followed by top-level domain servers, .com, .org, etc., then authoritative name servers for specific domains. When you type a URL, your computer checks its local DNS cache, then queries a DNS resolver if needed. DNS uses various record types, including a record's IPv4, 4 times a record's IPv6, and MX records, mail servers. Now let's see how multiple devices can share a single public IP address through NAT. Network Address Translation, or NAT, is a crucial technology that allows multiple devices to share a single public IP address. It works by modifying network address information in the IP header of packets as they pass through a router. There are different types of NAT, including static NAT, which maps private IPs to public IPs one-to-one, dynamic NAT, which uses a pool of public IPs, and port address translation, which maps multiple private IPs to a single public IP using different ports. NAT not only helps conserve IPv4 addresses, but also adds a layer of security by hiding internal network details. This technology has been instrumental in extending the lifespan of IPv4 addressing. Now let's explore how networks prioritize different types of traffic with quality of service. Quality of service, or QoS, is a set of technologies that work to manage network traffic and ensure optimal performance for critical applications. It becomes especially important when network capacity is limited. QoS looks at several key parameters including bandwidth, the maximum rate of data transfer, latency, the delay before data transfer begins, jitter variation in packet delay, and packet loss, data that fails to reach its destination. Network administrators use various QoS techniques such as traffic shaping, packet scheduling, and congestion management to prioritize certain types of data over others. For instance, in a corporate network, video conferencing data might be given priority over file downloads to ensure smooth communication. QoS is crucial for applications like online gaming or streaming services that require consistent network performance. Now let's look at how networking extends beyond physical infrastructure with cloud networking. Cloud networking represents a shift in how we think about and implement network resources. Instead of owning and maintaining physical network infrastructure, organizations can now host some or all of their network capabilities in cloud platforms. This approach offers several service models, including infrastructure as a service, platform as a service, and software as a service. Cloud networking brings benefits like scalability, allowing easy adjustment of resources as needs change, cost-effectiveness through pay-as-you-go models, and reduced maintenance as the cloud provider handles much of the upkeep. Key concepts in cloud networking include virtualization, where physical resources are abstracted into virtual ones, software-defined networking for more flexible network control, and network function virtualization, which turns network functions into software that can run on standard hardware. Now let's explore how everyday objects are becoming part of networks in the Internet of Things. The Internet of Things, or IoT, represents a significant expansion of networking concepts to everyday objects. IoT refers to the network of physical devices embedded with electronics, software, and network connectivity, allowing them to collect and exchange data. These can range from simple sensors to complex machines, including items like smart home devices, wearable fitness trackers, or connected cars. IoT networks face unique challenges, including managing power consumption for battery-operated devices, ensuring security across billions of connected devices, and maintaining interoperability between devices from different manufacturers. To address these challenges, specialized protocols like MQTT and CoAP have been developed. The IoT is driving innovation across various fields, from smart cities and agriculture to healthcare and manufacturing, opening up new possibilities for data collection and analysis. If you are able to master cloud networking or IoT, you are most likely to earn significantly more, as these are specialized fields with very few professionals and there is huge demand in the market. Now let's look at how we solve problems when things go wrong with network troubleshooting. Network troubleshooting is the process of identifying, locating, and resolving problems within a network. It's a critical skill for network administrators and involves a systematic approach to problem solving. Common tools used in troubleshooting include Ping for testing connectivity, Traceroute for showing the path data takes through the network, Netstat for displaying network connections, and Wireshark for detailed analysis of network traffic. The troubleshooting process typically involves steps like identifying the problem, establishing and testing theories about the cause, implementing solutions, and documenting the process for future reference. As networks become more complex, automated troubleshooting tools employing artificial intelligence and machine learning are becoming increasingly common, helping to predict and prevent issues before they cause significant disruptions. Finally, let's look towards the future and explore emerging trends in networking. The field of networking is continuously evolving, with several exciting trends shaping its future. The rollout of 5G networks promises faster speeds and lower latency, paving the way for new applications in areas like autonomous vehicles and augmented reality. Network automation and artificial intelligence are making networks more self-managing and efficient. Intent-based networking is emerging as a new paradigm where networks can configure themselves based on the desired outcomes specified by administrators. Edge computing is gaining prominence, bringing data processing closer to where it's generated to reduce latency and bandwidth use. Technologies like network function virtualization and software-defined networking are making networks more flexible and easier to manage. Looking further ahead, quantum networking holds the promise of ultra-secure communication. As our world becomes increasingly connected, these networking technologies will play a crucial role in shaping our digital future, enabling new innovations and transforming how we interact with the world around us. This concludes our journey through the basics of computer networking. Remember, this field is vast and constantly evolving, so keep learning and exploring. And don't forget to like, share, and subscribe.